Editar el video, se va a los usen.
Ah, bueno.
Acá.
Yo creo que se podría comenzar.
Está todo listo. Ahí está. Y esto lo oculto para ahí y el puntero.
¿Y las salas contiene espera o automáticamente la gente apenas-
Automáticamente entra. No,
Ah,
nadie
excelente.
tiene que hacer clic, nada. Así que por eso te digo, déjalo grabando y la gente se lo entra. Tú no te preocupas de nada con este computador. Si
Entiendo.
quieren mutear o quieren parar la conversación, no se va a acoplar, pero llegar a ocurrir el misterio y se activa.
Sí.
Así que eso, no hay mucho más que agregar, ya estaría todo montado.
Muchísimas gracias,
No te
Daniel.
preocupes, sí, por eso vine un poquito antes para que estuviera lista la hora.
Y sí, otra cosa que quiero preguntar entonces después de que termine de grabar, en tu computador me imagino que hago igual que la vez pasada, lo pongo acá adentro, lo guardo acá
No,
adentro. Ah,
déjalo
no es
ahí,
ahí, es tal cual
sí,
ahí.
yo vengo a dar una
Sí.
vuelta después a desmontar todo.
Y
Sí,
después entonces copio la grabación o en una
ahí claro, lo podemos
foto.
juntar para de nuevo con un pendrive, yo lo copio y te lo paso.
Ah, perfecto.
¿Ya? Así que en
Sí.
ese sentido tú no te preocupes.
Muchas gracias, Daniel.
Ya, que te vaya bien.
Que estés muy bien.
Igual, ahí está el puntero por si acaso. Buen día.
Gracias. Un recordatorio, otro recordatorio.
Sí, sí. Hay que ir a buscarlo arriba.
Sí. Bueno, ya viene. Hola. 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 Hi. Hola. 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 Bien, gracias.
I did. Did you get the email about this? I did. Because I did not.
I told all the people, you know what, all the list of the seminar. So we check. I put all the. Have you received the email from the message from the previous seminar?
I always ignore them. Sorry.
You always did?
No, they never on the list.
You are in the list.
No, my name is in the list.
Okay, your name is.
Anyway, I brought over all the troops I
I think
could.
we'll start.
Yeah.
Yes, and
No, no, I do mostly like physics. Yeah, no, yes. This is like, okay, I have some interest in this, but actually I decided to do this seminar because I think it's like I'm more closer to like a high energy physics and stuff like that. Typically I do something a bit different.
Heavy ions.
Heavy ions, yeah, but this is also about this is heavy ions, just different kind of view.
some people will connect via Zoom.
Yeah.
Están en 2 minutes.
We have a great view from here, you know, like
Yes.
outside.
Are you visit all the part of the university? Did you visit the part in the?
I mean, sometimes I go like around a bit. And it's like a nice district, it's like a quad. Campus is beautiful.
Yes, very nice.
I actually didn't like explore the city a lot itself, but I spent last 5 days and the holiday period here. I went to Atacama.
That's great.
I spent there like 4 days visiting like in mountains mostly. So it was nice.
Very nice.
We start on
I
time.
think, yes, I think now we start. Good afternoon. We are very happy to have here Martin Rybar, who is an international recognized expert in heavy ion physics, experimental particle physics, especially heavy ion physics. And today, Martin Rybar from the Charles University in Prague will talk about collision of light at the LHC. Thank you very much, Martin, for accepting the invitation.
Yeah, thanks for the invitation and you for coming. I apologize, it will be in English. My Spanish is super bad and it will be very, very short seminar. Maybe it will be better for you, I don't know, we'll see. Okay, so I am going to talk, I want to say that the title of the talk is a bit like a clickbait, like a collision of light at the LHC. But maybe it's not that. We'll see. So I'm going to talk about like an area of physics that is really like rapidly growing, and it's the idea is that you can basically use like a proton-proton accelerator or heavy ion accelerator to actually collide beams of light, and that's what I'm going to show you in this seminar. And I will mostly focus not on using the PP collisions, but actually to use the heavy ion collisions. So like typically like at LHC, we mostly collide lead ions, but LHC provided these heavy ion collisions since 2010. And we collided not only the two lead ions, but also there was like a short runs of xenon collisions. We collided proton and lead, and actually this summer, I mean the summer in Europe, we collided oxygen and neon and proton with oxygen. Here you have some information about the center of mass energy, but this is not what is important. So the usual stuff that you do with these heavy ion collisions is that you study the nature and the properties of very hot, like an extreme matter that we call the quark-gluon plasma. So if you take like these two ions, could be like two lead ions, and you smash them together in this like an overlap region, you deconfine the quarks and the gluons that are normally bound in the protons and neutrons, and you create this like a quark-gluon plasma here, which is like basically it has a temperature that we think was here like a microseconds after the Big Bang. And it's a great laboratory to study like a quantum chromodynamics. So this is the usual stuff what you do in the collision of the lead ions in CERN or in collisions of the gold ions, for example, at the Rick accelerators in States. And typically what you measure, like how you try to understand what's going on in these ion collisions, is that there are like two types of measurements. So the first one is that you create this like this volume of this like a quark-gluon plasma that of course doesn't sit there, it expands, and it actually is really interesting that you can describe it using like a hydrodynamics. And then I mean it expands, it cools down, it turns into the particles, you detect them, and there are some correlations and fluctuations, and based on that you can this is like the evolution of the time of this medium, and you can learn something about the properties of the medium. That's like one way how to study, how to do this usual physics of ion collisions. Second thing is like a tomography, right? If you want to do a tomography of your body, what you do is that you go to a hospital, right? They will put your body into like into X-ray, and you have a photons going one side, and the other side you will detect it, and then you will understand what is inside you. With a quark-gluon plasma, you cannot do this easily because I mean it doesn't stay there. I mean the lifetime is super short, so there is not enough time to have like an external source of something to tomograph the medium. But actually, you can use some internal processes that sometimes in the middle of this hot and dense medium, you create some other particles that penetrates it from the inside. You detect them, but those particles interact with this quark-gluon plasma, and again, you can understand something about the properties of the medium and about the strong force. So this is the classic. This is the usual physics that, for example, I have been doing since basically all my PhD. But this is not what I'm going to talk during this seminar. I'm going to talk about this like a very specific types of collisions that I will describe a bit later. But maybe let's just look how these collisions at LHC, how do they look like, how busy they are in terms of like a particle productions. So first, I mean, if you have just standard proton-proton collision, it's I mean, at first look, I mean, you have the two protons that you collide, but of course, you actually don't collide the protons themselves, but you collide the constituents of the protons, so the quarks or gluons, and you create something, right? But this is the simple picture, because I mean, these protons are complicated object. The collision gets like kind of messy. You produce like a lot of stuff in this collision. So you have some radiation from this final state. You have some radiation of like a gluons from the initial state, and you produce like a lot of particles. So this environment is much busier than, for example, if you collide electron with positrons in some other accelerators. Then, additionally to this mess from a single PP collisions, if you are actually running LHC, you don't collide single protons, but you collide so-called bunches of protons. And at a single collision of these bunches, these days we have up to like 60 different proton-proton collisions that you can see here. So you have like one collision, another one. You have the particles that are flying from the basically like from almost one space, one spot in the detector, and you have to have the ability to reconstruct all these tracks and associate them with these different vertices. So actually, even the simple proton-proton collisions, the environment is quite busy at the LHC. You produce like tens or even up to hundreds of particles in these PP collisions. And then if you go to this standard heavy ion collision, so you really smash the ions, you can produce up to thousands of particles. So this is like the Atlas detector, how it looks if you have like a central, so you have ion and ion, and you really collide like a head-on. You produce up to 100 particles, up to 1,000 of particles that you need to reconstruct with your detector. So these collisions are very, very massive. Okay, and this brings me to description of the geometry of these heavy ion collisions. Because sometimes, you have if you collide two ions, you have a different overlap between the collision. So you can have a peripheral collision, when the overlap between the two ions is very small, or you can have like a very central collision where the collisions are where the two ions are collided like a head-on. Okay, and of course, if you have more central collisions, you produce more particles. So I mean, as I said, in the central collisions, this is the particle multiplicity, so how many particles you produce in heavy ion collisions. So you can produce up to like a few thousand of particles. And in the peripheral collisions, which are here, you produce only like tens or like only a few particles. And this is all controlled by this impact parameter B, which is just the distance between the centers of the two ions. All the soft processes, so the number of particles produced in the collision, is basically depends on like how many participants you have. So the number of participants is the number of nucleons here and nucleons here in the overlap region. But actually, number of hard processes, like if you produce like a top quark or a Z boson and these stuff, that actually scales with the number of binary collisions, because one proton or one nucleon from one ion can actually hit like a multiple nucleons from the other nuclei. Okay, so that's kind of like how you can imagine the geometry of the ion collisions. And we cannot measure directly the impact factor B, because these are like at the level of femtometers, and Atlas cannot, or any of the detector cannot measure the distance between the two ions simply. But as I said, if you have like a central collision, it means that you produce more particles, so you have more energy in your detector. While if you have a peripheral collision, you produce less particles, so you have less energy in your detector. So we actually measure, like this is the measure of the centrality of the collision. So if there is a lot of energy, which we actually measure only in some parts, like a very forward region of the atlas, if there is a lot of energy, we say there is large overlap between the two ions, and these are central collisions. While if there is only a few particles, small amount of energy in the detector, these are these very peripheral collisions with only a small overlap between the ions. Okay. And now you can ask whether we actually understand this geometry, how we can prove that we understand this somehow. So again, it's like a normal heavy ion collision. When you have these overlaps, you can start to measure like probabilities that you produce some particles. Nice example is that you start to measure a cross-section, so probability distribution that you produce a Z boson. You can do it also with the W boson. The nice thing about the Z's or the W's is that these are electroweak or weak bosons. So they actually don't interact with this quark gluon plasma that is created when you smash the ions, because that is dominated by the strong interaction. So if you measure the yield or the cross-section in the lead-lead collision, and you compare it with the cross-section measured in PP collision, and you just account for some simple geometry scaling, that here you have like a more binary nucleon-nucleon collision. This ratio is called RA, nuclear modification factor. This value should not depend on the centrality. That's what you can see on this plot. So this is the RA, okay? So this is this factor, and it's plotted as a function of the number of participants. So here you have the peripheral collisions, here you have the central collisions, and you can see this RA is basically consistent with 1, which means that we kind of understand the geometry of the collision, because this is like a model dependent, and this geometrical factor, and everything works just fine. So this is just an example that we really know how the geometry works in the ions, and we can measure things. So this was like a bit of introduction what we normally do in the ion collisions. And now I will actually switch the gears, and I will talk about this main topic of this seminar. And that's actually, these are the collisions where the two ions just misses each other. So there is no overlap region. So what actually happens? Right? I mean, they miss each other, so there is no interaction, right? But that's not true, because you have the electromagnetic fields around the ions, and those fields can interact. Okay, because you have a lot of charge here. In the lead ion, you have 82 protons, so there is a lot of charge. So there is an EM field around that. And the thing is that because these ions have basically speed of light, they are, from the lab point of view, they are Lorentz contracted, and that actually changes like what is the strength of the field. And actually the strengthness, so the magnetic field is like a very, very strong. So you get like a local field up to like a 10 to the power of 15 Tesla. Okay. if you have such a strong field, you can use some approximation. And what you actually get out of that is that you can imagine that you have the flying ion, which is accompanied by a flux of the photons. So like you have an ion, and then you have a flux of the light that is basically around the ion. And these photons are basically nearly real, and they have quite high energy. So you can actually use these so-called ultra-peripheral collisions. So it's not even peripheral, it's ultra-peripheral because you have no nuclear overlap. And you can use this as a laboratory to study quantum electrodynamics, actually to do a precision QCD, which I will show later, and also to use it for some Bion standard model searches. So maybe a bit more like the theoretical description of these processes. So as I said, we are colliding, it's like they are Lorentz contracted, so they are basically pancakes. It modifies the EM fields, and at the end, as the result, you have basically the flux of the photons. These photons, they have a very small transverse momentum scale, and at the LHC, their momenta, so energy or K of the photons, is up to 80 GeV. This is at the LHC energy. So what you basically get if you accelerate these ions, that you don't get only the ions, but also you get a large flux of the photons up to 80 GeV. The energy of the photon actually depends on the distance from the ions. So again, if you have the two colliding pancakes, these are the ions, and the highest energy photons, they are close to the ions. And if you are going further and further apart, the energy of the photon is decreasing. And so at the LHC, if we accelerate the lead ions, and you have the collisions of the two photons, so we have one photon from one ion is interacting from the photon from the other ion, you can get in the center of mass energy up to 170 GeV. You can also have an interaction of the photon with the ion itself. So it's not photon-photon interaction, but photon-ion interaction. And there you have energy up to 700 GeV. You can also study these processes in like PLED collisions or PP collisions. But I will not discuss this in a detail right now. Or also can find like other accelerators, energies that are calculated for other accelerators in this table. But just to have some rough idea, what is the energy that you can get in these photon-photon and photon-ion collisions. So if I go back to this, what is the photon flux? So people typically use this Weizsäcker-Williams approximation or approach. So this is basically the photon spectrum. So the K, that's the photon momentum or energy, and the P is the impact factor. So it's the distance between the two ions. And then you have like all the classic kinematics formula and the K's. These are just the Bessel functions. What I want to just make out of this formula is that if you want to calculate the total flux, you basically just integrate this over the B, and you just have to remove the situation when you have the nuclear overlap, right? So you just want the collisions where actually these are ultra-peripheral collisions, so you don't have the overlap. So this is like a probability of no hadronic interaction between the ions. So there's some geometric of factorials. Now what is important is, okay, so first this is a picture of the spectrum of these photons. But if we go back here, you can see that the spectrum scales with the z squared, okay? So with the charge of these colliding objects with the power of 2. Which means that the cross-section for the collision scales with the power of 4. And that's actually why it's important, or that's actually why we benefit from using the lead ions, because you have a charge of 84, and the cross-section then scales with the power of with the factor of 84 with the power of 4. So that's actually why it's beneficial to do this in in these heavy ion collisions rather than in PP collisions, because of this a huge scaling in the cross section. Okay, so this was a bit of introduction, that. Okay, you have ions, you have the flux of the photons around them, and these photons can collide with each other or with the ions itself. And now, why this is interesting? What you can do with this? So first, actually, you can really test the standard model. So you can test the precision of a quantum field theory, or actually you can do some direct searches for new particles beyond standard model. You can really test its basics of the quantum electrodynamics, and you can get really super nice processes where from the collision of the two protons, so from just pure energy, you can create a matter in form, for example, of the electrons and the positons. Then it's important for if you want to understand any extreme environment where you have a large density of photons with for example, if you have some a cosmological objects these active galactic cores and so on, where you have a lot of light and the light can interact with itself with another sources of light, or for example, if you want to understand there can be some impact on the cosmic microwave background and so on. Then you can actually use these photon-ion collisions to try to understand the structure of the ion itself. And then, I mean, it's you can search for processes like scattering of light on light. So basically doing something like lightsabers in from the Star Wars. By the way, the lightsabers, this interaction is not possible in the classic theory. So if you have Maxwell equations, they are linear in the field, so you cannot have the light by light scattering. You have to go to QED basically to have this process. Okay, so now let me actually walk through these processes that we are interested in and what we can why we measure them. So I will start with these gamma-gamma photon-photon interactions. So the first thing is that you can collide the two photons, and you can just create leptons. So you can create muons or electrons. And so first thing, if you do such a measurement, you really calibrate the photon luminosity. I mean, you test this calculation of this like a simple approximation of what is the flux of the photon, if you understand that. So that's why you measure these things. Of course, it's like a basic test. These are basic tests of the quantum electrodynamics. You can tune the models, but you can also actually use this to study some beyond standard model stuff, because this cannot be just a normal photon, but can be, for example, some like a dark photon from some BSM extension. If you produce here not a quark, sorry, not a lepton, but for example, two quarks, so we have a quark and anti-quark. These, of course, doesn't exist in nature just themselves, so they will fragment into some particles, and that's actually where the QCD enters. So you can actually use this like a QED laboratory, so the two photon interaction, and you can create like a pair of quarks that then fragment into something that we call jets, like a spray of particles, and it will be it can be really like a precision measurements of the QCD, because as I will show you later, this is like extremely clean signal. Okay, and then as I said, you can like really do like a precision testing of understanding of the quantum field theory and do some like a BSM searches. For example, by studying this process where you actually have a collision of light on light. So I mean, in terms of the Feynman diagram, it looks like that. So I mean, you have incoming photons, you have some like a box diagram, and you have the outgoing photons. I will discuss this a bit later. And this is how it looks like in the detector. So if you remember these pictures that I showed at the beginning, you know, where you had like tens, hundreds, or thousands of particles produced in PP collisions or in these like normal heavy ion collisions. If you look at these ultra-peripheral collisions, these detectors are completely empty. So this case shows this interaction when you have a collision of two photons and you produce an electron-positron pair. And this is the Atlas detector, and you can really see just the two tracks to the position of the energies in the calorimeters, and that's it. So it's like a extremely precise environment, and you can do like a precision measurements. And you cannot do this even in PP collisions because you have all these pile up and multiple interactions and so on. So these are the gamma-gamma interactions. Then there is this another class of measurements where you have an interaction of the photon, not with another photon, but with the other ion itself. And by that, what typically you do is that you study the structure of the other ion. Something that we call basically you study a parton distribution function. So you study like whether the proton or neutron, which is inside the ion, whether its structure is different, whether you have just the proton and the ion, like in the vacuum, so just the plane, just the proton or neutron alone. And then you can also like make like other processes. You can, for example, study, okay, this was like a production of some like a vector mesons, like a J psi, or you can again produce like a quark and an anti-quark, but with the breakup of the one nuclei, and again you can do some studies of the structure of the ions, or search actually for some signatures of the quark-gluon plasma, which I will also mention a bit later. And these interactions where you have this photon and an ion collisions, it actually also provides a nice bridge to the future electron-ion collider that is going to build in the US in Brookhaven National Laboratory. Because okay, so here you have a photon-ion collision, and here typically you have an electron, but it will be some sort of deep inelastic scattering. So you will have an interaction of the photon with the proton from the other beam. So the UPC is a very natural bridge also to this EIC accelerator collisions. And I showed you how the interaction of the gamma-gamma going to two leptons looks like. If we have this photo-nuclear collision, it typically looks like this. So here, again, you see the atlas. This is the beam pipe. Okay, you have two ions going, one from this side, one from this side. And in this case, you can see that the particles are produced this way, which means that the ion that was going here breaks and produces a lot of particles that are going that direction, while the one ion which emitted the photon survived and it's going this direction. So that's also how you can distinguish these signals in the detector. This brings me to some problems actually, like in measuring these processes. So this is a schematic view of Atlas. You have it also here. It's a beautiful, big, complicated system, but it is designed to do physics like, look for like measuring a top core, looking for Higgs boson and so on. And these are really like a high energetic particle objects. Okay, but I said that in these gamma-gamma interactions, you have like up to 160 GeV in the center of mass system, which is of course like a few orders of magnitude smaller energy than if you have a proton-proton collision. So all the stuff that are being produced in these collisions are also typically like an order of magnitude have a low order of magnitude lower energy than, for example, if you study processes in the PP collision. So we are really interested in measuring like a relatively low PT objects. By low PT, I mean like a few GeV electrons, few GeV photons, jets at 20 GeV, 30 GeV, and so on. And Atlas is really not designed for that, but actually it can be used to that. So how we actually detect these things? So I said that the two ions misses each other, right? And there is some interaction, and you see like a few particles in the detector. But how you can tell? And what is really a key is detecting the so-called spectator neutrons. So the spectators are the guys that do not interact in the collisions. Okay, so I mean, this is like a normal ion collision. You have participants, and these are so-called spectators. So the spectators just fly away from the interaction point. But what they do at some point is that they hit some other part in very forward of the atlas. I will show you later. So how we so-called trigger on these events is that first we look into the atlas itself, the central part, and we put some veto on the activity. So we basically require that there is almost like nothing in the calorimeter. So you put some veto on the number of particles or whatever. It must be very, very clean collisions with only like a few tracks, for example. And then you ask for some specific signal in so-called 0-degree calorimeter. Okay. So the atlas itself, I mean, it's like a 40 meters big detector, so it's here. But like 140 meters far from the center of the atlas, you have another detectors that are actually plugged into the atlas like a data acquisition system. And they are also called 0-degree calorimeters because they are really sitting at the zero degree, okay, with respect to like if I'm talking about this angle. Okay. The detector looks like this. So you put it in a place where the beam actually splits in two. So normally, if you cut the LHC pipe, you will see two tubes, and the protons are, they circulate in opposite direction in the two tubes. But approximately 140 meters far from the center of atlas, these two tubes they merge into one tube. Okay. And in this place where you have the splitting, you put another detector, okay? And then if you have these neutrons, these spectator neutrons that survive the collision, they continue, they were like flying still in the beam pipe. So then they will hit this point and they will hit this detector. And that's the way how you can detect these spectator neutrons. The problem is that this place is like a crazy irradiated, even if like a normal PP collision. So when you have to, I mean, if you install these modules and so on, you have to do it with like a robot and such. Okay, but it's like it's really nice detector. It's like a picture from like an installation from distance. And now, if you look what is the distribution of these or how these collisions look like. So this plot, it's very important. It's the same thing, it's just that there is a logarithmic scale and here is the linear scale. But it kind of shows you like what is here's the energy that you detect on one side of the atlas, here is the energy that you detect on the other side of the atlas. Okay. And it's calibrated such that the one is the energy of the one neutron from your lead ion. Okay, so as I said at the beginning, if you collide lead ions, in run 3 you have something like a 5.3 TeV per nucleon. So the one here means that you detect one neutron that has an energy of 5.3 TeV. Okay, so this is basically a detection of the one neutron. Here there is detection of the 2 neutrons, 3 neutrons, and so on. So if you are here, it means that you are detecting one neutron on one side and also one neutron on the other side. Here you detect 2 neutrons on one side, 1 neutron on the other side, and so on. So we typically divide this into a few categories, so-called like a X neutron on one side, 0 on the other. and the opposite, and then you detect like a multiple neutrons on both sides. Okay, so this is like how you categorize these events. You can actually project this on one axis, and you will see this. So as I said, so this is like a signal. If you have an event and you see 1 neutron, 2 neutron, 3 neutron, 4 neutron, and then you have some like a continuum, and then you saturate your detector. Okay, and now the question is like, what is the origin of these like of these peaks? Are these like very peripheral collisions, or like ultracentral collisions where few neutrons survive and they continue like in the beam pipe, or could actually be that these are these ultra-peripheral collisions, so where the ions misses each other, but you still see some neutrons detected in the forward region, and that's the case. Because what can happen is that there is really large probability that you have the two ions are passing each other, and they will exchange just very, very soft photon. Okay, but the soft photon will excite the one ion. There is something that is called giant dipole resonance in the photon neutron cross section, and if you do this excitation of the one ion, there was no interaction between the two ions like a hadronic. There was no overlap. You excite it with the photon, and then this excited ion decays and emits few neutrons, and you detect them in the forward direction. Okay, and here is just a plot that is showing the probability of this forward neutron probability. This is shows the forward neutron probability based on this impact parameter. How far are the ions? So of course, if there is an overlap, so the overlap is when the impact parameter is smaller than the two radii of the ions, then you have a huge probability that you produce multiple neutrons in both arms. This rapidly drops, but then actually you can produce a few neutrons on one side even if there is no overlap because of the effect that I just mentioned. Okay, so these events are actually not ultracentral collisions where you can also produce a few neutrons, but these are almost all these ultra-peripheral collisions, and that's how you can trigger on these or select these events for your analysis. Okay. And now I will move to some processes, okay, that I started to describe before, but I will go a bit more slowly through them and say why they are interesting. So the first one is this production of the two leptons. Okay, so you have this collisions of the two photons, and you produce pairs of muons or pairs of electrons. There are some backgrounds. As I said, if you measure a cross section, then you can be sensitive to any discrepancies with the theory that will give you. I mean, the theory, I mean just the simple quantum electrodynamics. For example, if you have emitted not the standard photon, but some beyond standard model dark photon. And again, here's like another example how in Atlas you can see, if you produce two, in this case, these are two muons. Again, like a super clear, it's better to visible here. You have nothing in the whole system, and just two muons flying apart. I mean, if you measure it, what you do is that, of course, you have, for example, diamond mass spectra, and you compare them with some model. In this case, it's a starlight Monte Carlo generator, and basically this gives you first is the QED. Can QED describe your data? Is your approximation that you use to calculate the photon plugs, is this correct? And actually, it kind of tells you that we understand this pretty well. So the QED is able to describe this, and also this simple Weizsäcker-Wilhelm approximation is also doing very good job. Then you can do the same thing in another channel. You can study not only two muons produced, but also two two electrons. You can do even more deeply. You can start to do some azimuthal, studied azimuthal correlation. This is more sensitive to like other processes, but I will not discuss this in a detail. What I actually want to show you, this is very interesting, is that this process, when you produce an electron-positron pair in these two photon interaction, it's actually something that limits the operation of the LHC. Because imagine that you have this collision, okay? So what you do is that you collide, of course, fully straight lead ions, right? So you, at the beginning, you have like a pellet of the lead ion, and then there are some multi-step system, how you remove all the electrons, okay? And then you accelerate this in the LHC, right? You cannot accelerate neutral objects. But then, if you have such a collision, and you create an electron-positron pair, the positron, then there is just, flies away. But the electron can be actually captured on one of the ions. So you will create not fully ionized ions in the machine, okay? And if you do this, and the problem is that this process has a huge cross-section. So the cross-section for hadronic interaction, that you have some overlap, is 7.7 nanobarns. The cross-section for this process is 281 nanobarns. So it's like a much higher than just the inelastic process. And what it means is that in the LHC, so this is the pipe of the LHC, and this is like some modeling of the profile of the beam. And what you do is that you create a secondary beam of the ions that is, it has different charge now. So it bends differently in the LHC magnetic field, and it hits the beam pipe. And the power of such process is actually that high that if the luminosity for the LHC reaches some point, you will put so much energy to this like a cryogenic system that you will quench the magnet. So basically this process limits what is the maximum luminosity that you can have for the LHC. It's coming from this UPC processes. Okay. Now, and another interesting thing that you can use actually this gamma going, for example, to 2 muons process to actually study quark-gluon plasma. Because so far, I've been talking about situation when the two ions misses each other, but the EM fields interact and you create 2 muons, right? But of course, these interactions will also occur in the situation when you have the overlap. So the ions overlaps, they create the quark-gluon plasma, but at the same time, also the EM fields will interact and you will create 2 muons. And now the one of the 2 muons can penetrate this volume of the quark-gluon plasma and can interact with it. Of course, it won't be a strong interaction, it will be some electromagnetic interaction, but you can actually do some very precision measurement with this. And this is one of the cool results from Atlas, is that we measure an acomplanarity, so basically the angle between the 2 muons. So we have 1 muon on one side, another on the other side, and they are almost exactly back to back in the direction. And if you take a model, the starlight that I showed before, the acomplanarity distribution should look like this. But actually now, if you measure these processes, so you have like central heavy ion collision, but you measure the muons that are produced like outside, you get much broader distribution. It's this, okay? But the problem is that the starlight, the models there are relatively simplistic. So the effect that we see here is not an effect of the quark-gluon plasma or some effect of that you have a strong magnetic field that is like somehow bending, the muons. But when theorists saw these results, they went back, they made like a precision QED calculation, and then by that you are actually still able to describe the data if you improve your AOR theory. Okay. Another thing, really nice, that how you can use these ultra-peripheral collisions when you produce two leptons, is actually that you can measure anomalous magnetic moment of tau lepton. So you probably know the anomalous magnetic moment of muon, which is one of the most precise measured and most precise calculated like observable that we have. The situation with the tau is much more complicated. It's difficult to measure it. But in general, if you have magnetic moments of any particles, it is sensitive to it can be sensitive to BSM models. So basically, I mean, if you calculate the magnetic moment, you have some like a three-level diagram that contributes to that, and then you have like other terms that basically modify the magnetic moment, and this modification that basically what is this anomalous part. So I mean, if you do the calculation without any BSM and you compare it to the measurement and you see differences, it can be a signal that there are some beyond standard model particles, like some leptoquark, supersymmetry, and so on. The advantage of using taus with respect to muons, where in the muons you have much better precision, is that, for example, the mass of the tau lepton can play a role, and there are some models when you have like a different coupling to taus with respect to muons, and in principle you can have, despite much better precision for mu g-2, you can have some advantages in doing this in tau leptons. I will skip this. This is like an Atlas event, again, like where we think we detected the production of the tau meson in the PC collision. So again, it's like a very, very clean, but the tau decays in a few particles. So we actually see like not only like a 2 as before, but now you see multiple tracks. And based on that, you can do some comparison of the cross-section of the anomalous magnetic moment and compare it to the theory. So this is like a state of art. So you have some like old measurements from E plus E minus collisions, mostly from lab. So these are these guys. Okay, so you have like the measurement and the uncertainties of the anomalous magnetic moment. This line, this is the standard model prediction. Now you have these two measurements this is the Atlas one from 2023. At the time, it was the most precise measurement of the magnetic moment of tau lepton. This is from these gamma-gamma interactions. And recently, CMS, they beat us because they were actually able to measure this super precisely, as you can see here, because they did gamma-gamma interaction, but they were able to do it in PP collisions in this high luminosity, high pileup environment. But they developed some method how to do it, and this went to this like a very, very precise measurement. It's still gamma-gamma interaction, but it's in proton-proton collisions. Now let me move to the light-by-light scattering. So this is this lightsabers, right? So as I said, this is not allowed in classic physics. It's possible in QED, but you have to go to the loop. So it's very rare process. So the cross-section scale with the alpha square, and it makes it like very difficult to be observed in like a laser experiments, where normally you would expect like when you want to collide light with light, go to laser. No, because I mean you don't have a lot of energy, so you have to do there are some workarounds. But actually you can do it in the heavy ion collision. So you have these near real photons that interact, but they have to interact through the box. Okay, because you don't have in QED you don't have a vertex with like a four photons. And so first this is testing, of course, the quantum electrodynamics, but also it's sensitive to BSM stuff, because you can have theories that, for example, predicts that there is an axion-like particle that would modify the cross-section by diagram like this. So we have two incoming photons producing the axion, and then that would basically decay into another two photons that you would detect in the detector, and that would modify or measure cross-section. We have some backgrounds for the events we will not discuss. This is how it looks in the atlas again. So basically now it looks very similar to the electron production, but now we are missing, of course, the tracks. So you see only the calorimetric clusters. So these are the two back-to-back photons. And this is the measurement. So I mean, you have the data. These are the black points, and then you compare them to your standard model predictions. So you have what you predict as the signal, what you predict as a couple of these backgrounds, and then if you integrate, you can get the total cross section. So basically, I mean, in the signal region, you see something like 100 events only, but even that is enough to basically say, okay, we observed for the first time the light by light scattering. And if you compare again with the standard model, I mean, the measured cross section is like 120, but with large uncertainties. We compare with some theories, and it's like a plus minus couple of sigma, like in agreement with the theory. So unfortunately, like we don't see any beyond the standard model signal in this light by light scattering. But it's still nice just be able to actually measure this process. But of course, if you do this, you can put some limits on these axion-like particles, for example. So I mean, this is like the section used to be state of art. I think that now this is from 2021. So you kind of see that here you have the mass of the axion particles. Here you have the coupling of the axion particles, and you could see like various different experiments how they contribute to excluding, you know, the phase space for the axions, and the two gamma measurements from CMS and Atlas, they basically contributed to this area. So we see that like nothing is here. It's maybe. You can also use the gamma-gamma interactions to search for magnetic monopoles. At the beginning, I said that you have super strong magnetic fields. You might know that if you have super strong electric fields, you can create through a Schwinger mechanism, you can basically polarize the vacuum, and you can create like electron-positron pairs. You can do something similar. Basically, you can create through the Schwinger mechanism, you can create an electric charge. Okay. Here, the idea is that if you have super strong magnetic fields, you can actually create, if there are magnetic monopoles, you can actually create them. Okay. So this is the diagram. So you have two photons, and you create like a magnetic monopoles. And then what would be the signal actually? So if you create a magnetic monopole, it would fly through your detector. It would be probably like a very heavy particle, and it would be also super ionizing. So I mean, here what you can see, these are like it's maybe better visible here. We have different layers of Atlas detector, of the pixels, the tracking detector. And normally you see like a few hits, and the particle, you know, that if you have electron, it would fly here, and it would leave like one of this dot here, 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 and here, plus some background. If you would have this like a magnetic monopole, it would ionize the detector like hell. And you will basically see this. So you have like one monopole going this way, one monopole going this way, and a lot of signal in the detector. So this is not simulation, this is data. So I mean, there was a search in the ion collisions. We saw two such events with this lot of ionization, but unfortunately, you can't expect like 1 plus minus 2 events, because you can have some. You know, if you see something like that, it doesn't mean that you see a monopole. There are another ways how you can create such a crazy event. So it's kind of consistent again with the standard model. And what you can, if you do these measurements, you can put some limits. I mean, here it's calculated for the monopoles with this like 1 unit of the magnetic charge, and you put like some limit again on like a monopole with some mass and with some cross section. So again, unfortunately, like we haven't observed yet magnetic monopoles. And the last topic that I will just briefly cover, or actually maybe one more after that, but we'll see where I am in that with time, is actually how we can use these gamma ion interactions. So I'll switch the gears a bit to understand the structure of the ion itself. So if you remember how scientists in the past understand the structure of the proton itself, it was through the deep inelastic scattering. So you have a proton, you have the electron basically emitted a photon, the photon interacted with the proton, and based on the scattering of the electron and the rest, you could basically measure the kinematics, and you could say, okay, there are quarks within the proton. You can do the same thing, but now when the photon strikes the one ion, and based on the wavelength of the photon, you can go deeper and deeper into the structure of the ion, okay, or of the proton within the ion, which might be different than just the proton that is in the vacuum. Okay. Here, the situation is again a bit more complicated, because actually photon, while maybe for students might sound weird, but it has an hadronic component. So you start with a photon, but the photon can fluctuate into, for example, QQ bar, so into quarks and anti-quarks. Yeah. Then another quark can emit a gluon. Okay. So you have like so the photon itself is actually a very complicated object. Okay. So you start with something like a photon, and you end up with some basically vector method, with like a rho, phi, or something like that. Okay. So basically, this interaction at the end might not be only a photon-ion interaction, but you have a photon that will basically change into, for example, phi or rho meson, and that will actually hit another ion. Okay. And if you do this, you can basically try to understand what is the structure of the ion. Okay. So normally, when we describe the structure functions of the protons or the ions, we can use this diagram where here you have the Q, the Q square of the hardness of the process. Here you have the description of the structure of the ions of the protons in terms of the X. And then if you have different probes, you can study different phase space in this plot. Okay. And if you are in this region, so you have you are looking for quarks and gluons within your ion or within your proton that carries a very small fraction of the total ion or proton momentum. You can have so many gluons there that you will reach something that is called a gluon saturation, when basically you have this splitting of gluons, but the rate of that will be the same as the recombination. So it's something that people try to look for quite some time. It's like a gluon saturation or onset of like a nonlinear QCD effects. And again, you can use these like ultra-peripheral conditions for that. And there are a couple of processes that we are interested in. So we can measure like a digest production that will cover this part of this phase space. Now, I realize it's a bit confusing because here there was a Q here and the X here. Now we have X here and the Q square here. But okay, sorry for this. But in general, you can do you can use different processes to cover different regions of this phase space. Okay, so you can use the digest production, the spray of particles, to cover this region. You can measure, for example, D mesons, open charm, to cover this region. Then you can measure production of different particles, like epsilons, J size, phi's, rhos, that are sensitive to different regions. And you can scan and you can understand the nuclear structure.
Excuse me?
Yes.
Can you go back?
Yes.
You talk about non-perturbative, you're
Yeah.
thinking in the color glass condensate or in this non-particular regime?
No, this is more like actually the production of these particles, like in terms of the non-perturbative. Yeah. Yeah. The nice thing about, for example, when you have a J psi, you are at the scale where actually you can, the production themselves is meant to be like that you can describe them as the perturbative production, not for these guys. Yeah, so for example, the J size, or okay, in general, like you have some vector meson, but with the J size, it's nice because you have this like a hard scale, it's perturbative. But if you have actually, so this is this process. I mean, okay, this is gold, but it can be lead. It doesn't matter. So you have the photon that turns into basically J psi, and you want to measure the J psi in the final state. To be able to do it, you have to have this like a two-gluon interaction, and this really enhances your chance of basically studying the gluon saturation. I won't go into the detail, but this is like one of the greatest probe, like if you measure J psi, how to basically be sensitive to the gluon component of your ions. Okay. This is how it looks like in Atlas. If you have a J psi in EPC, so I mean J psi then splits in like some dielectron pair. These are electrons. And yeah, again, like a super clear signal. This is nice measurement from Alice, where actually you can kind of see that we understand the J psi production very well. So I mean, we have the measured distribution, and then you have various components. We'll not discuss in details that contributes in the production mechanism of the J psi. But at the end, we are able to describe them really well. Okay. Photonuclear, I will just skip it. It's complicated, maybe a bit more, and I don't have the time for that. But I would like to mention one last topic very briefly, and that's actually how we can study the quark-gluon plasma in these ultra-peripheral collisions, which might be like a bit weird because at the beginning I said these are collisions where actually there is no overlap between the ions. We don't create the quark-gluon plasma, so how we can actually study the quark-gluon plasma. And I will start with just very small, short motivation. So at the beginning, I said that we have these two classes of these classic measurements in heavy ion collisions. We have these penetrating probes, this tomography. And then we measure the correlations in the particle production. And the correlation in the particle production actually came or comes from the initial geometry of the collision. So imagine that you collide the two lead ions, okay? So in the first approximation, you collide two, I mean, if you look, there are pancakes, right, flying like this way. So from your point of view, there are two circles flying that way. And you will have overlap region that will look like it will have an elliptical shape, okay? This is the first approximation. Of course, you don't collide pancakes. There are nucleons that fluctuate. So this shape of the overlap region is more complex, more complicated. But the thing is that the volume of your quark-gluon plasma at the beginning is somehow proportional to this shape of an overlap region, right? Because that's where the ions collide, and that's where you create a quark-gluon plasma. But because it's not fully symmetric, you have some pressure gradients. So for example, if you have this like elliptical shape like this, you have more gradient in this way than in this way, which means that you produce more particles this way than this way, and this will create this like anisotropy in the particle production in your detector. Okay. And this anisotropy depends on the properties of the plasma, whether it behaves like more like a fluid, more like a gas, with the coupling between in that and so on. So this is like you can learn a lot basically from studying these correlations. And it was one of the most striking feature in these hadronic heavy ion collisions. This was one of the features how we were able to say that actually there is a quark-gluon plasma produced in these collisions. Okay, so the message is that the anisotropy in the shape of the plasma, how it expands, is then translated to the anisotropy in the particle production. Okay, and now the question is, what is the smallest system where we can actually see this collective behavior, this anisotropy in the particle production? So we have seen this in the collisions of lead ions, gold ions, xenon ions. Now we saw it also in the oxygen ions. But we actually also see it in the collisions of the proton and ion. So when you have the pancake, which is hit by the proton, but even proton has some size, and we see the collectivity there as well. So we actually produce this flow behavior, this correlation in the P-lead collisions. Then actually what was super interesting is that people realized, okay, so maybe we can look actually in PP collisions, and you see there as well. So you see the flow, the collectivity, so possible sign of like creating droplets of quark-gluon plasma in some specific PP collisions if you select them based on like a particle multiplicity. Like basically you can have like also some sort of like a centrality collisions. Then people went back and they look at the E plus E minus collisions. And it would be really weird if there is some flow and there is no flow. Okay. So there is no flow. And now the question is, how about the UPC? Can this be the smallest system that flows? Of course, if this would be a collision of the photon with the ion, there should be no flow. But as I said before, a lot of these interactions are actually not a photon with the ion, but there is so-called like a vector meson dominance. So the photon fluctuates in some other state, and that hits the ion. So it's not like a proton-lead collision, but it can be like a rho and lead collision. Okay. The question is, do we see flow there? The flow is usually expressed by this V2. So the V2 is somehow size of the modulation in the particle production. And if the V2 is 0, it means that there is no correlation and there is no flow, and then probably there is no quark-gluon plasma. And here, you can actually see the measurement in these photonuclear collisions as a function of the PT of the particles. And you see that the V2 is non-zero. Okay. So we actually see this is the smallest system where actually we see the collectivity. But there are also like some models like core glass condensate that basically can also predict basically the non-zero Okay. And you can compare the flow with like this is in the UPC collision with the flow in PP collisions where it's a bit higher. And if you go to P-lead collisions, it's even a bit higher. Okay. So this is really the smallest system so far where we have seen the collectivity. So this brings me to the conclusion. So the main message is that actually the LHC can be used as the photon collider, not only a heavy ion or proton-proton collider. And it kind of bridges the world of the heavy ion physics and the world of the standard model and the world of like beyond standard model like physics. Because there is like extremely rich program and many ideas what you can do with this UPC, and it's really like expanding. And I mean, when LHC started back in like 2009, 2010, we had the first ion guns. We actually didn't like, there was no, there was no interest almost in, there was one guy I remember who was like interested in UPC, but we almost didn't take any data and no triggers and nothing. Then it's changed like a few years ago when there was the like explosion of the ideas. And now, like this is a really significant part of the heavy ion program. So, for example, CMS detector, the collaboration is now, I would say, maybe 50 or maybe even 70% moved from this classic heavy ion physics to this like physics of ultra-peripheral collisions. And this is great because now actually people are thinking more about this, and we can optimize the data linking strategy and so on. We are in the middle of the run 3, and the focus is really on this stuff, and the precision of all these measurements will increase, and maybe we'll see something interesting. So that's all. Thank you very much.
Thank you very much, Martin, for the very nice and very excellent complete talk. Question from the audience? Will?
Yeah, so the ZDC, so there are basically quartz fibers inside the ZDC. And so the biggest problem for ZDC is that I think it was after the run 1, it stayed. So usually the operation is that you have the 1 month of lead heavy ion taking. So you put the ZDC there just before the run. You run the heavy ion program, and you take it out. Because during the PP operation, in PP, I mean, you have so large luminosity that the radiation is like a crazy in that region of LHC. And I think it was during the run 1, the ZDC was left there after the ion run, and it was left there for the part of the high luminosity PP data taking, which made it basically almost like a blind. They took it out, and the quartz fibers that are like, they should be like clear, they were like completely dark. There was some like, like after some time, the quartz like cleared a bit, but they had to refurbish it. So for run 2, the ZDC was basically completely replaced by the quartz fibers, but there was also like a lot of new electronics and everything, new cables and stuff like that. But it's super important that it's now there only for the ion operations, and then you take it out, and it's not there for you. There is also a project for high luminosity LHC. There was a lot of ideas how to use like what materials to use. There are even some ideas with some like mineral oils and so on that you could like change basically on the fly. I think there is a common project with the CMS basically, but I am not expert on it. But there are some plans for the run 3. And also actually now the ZDC has, so the ZDC is a calorimeter, so it has like 1 electromagnetic module and 3 hadronic modules. But in run 3, they also added something that is called reaction plane detector in front. So you have like some granularity not only in this direction, but also in this plane, this like that you can measure the reaction plane.
Any more question from the audience?
So you mentioned that you can have this EM collision, produce electron positron, and one of ion will capture one electron.
Yes.
Can you have that with muons? I have a muon.
Yeah, I know, like that you capture a muon on that. Sure, you can have. I don't know what is the cross section for. First, the cross section for the muon production is smaller. I think a little bit smaller. But yeah, okay, it is energy very similar.
Last time is very small, but
okay. Yeah, maybe. Maybe discuss this later and find the answer.
More question?
You talk about that you can use this photon in order to study this chloroplast idea. But is enough energy for this, or transition from to
Yeah, I mean,
celebration regime.
yeah, I mean, so
Any comments about it?
yeah, I mean, so for CGC, yeah. So I mean, you will have like a small x, right? I mean, we have a lot of theories that will try to explain, you know, the same. Maybe okay if I go to maybe jets. Yeah. So I mean, for example, for jets, if you measure like jet cross sections or jet mass spectra and so on, and if you are, you know, in like some like a very small x, then you are sensitive basically to these effects. Okay, like to the effects that are like the guys from the CGC, they will make some predictions, and then you will have someone with just, you know, like a gluon saturation, and they will also try to predict. With the CGC, it's like so I remember like back like, I don't know, 7 years ago, I was doing some measurement in P-led collisions, which in some of the production of the jets in proton-led collisions in forward direction. So it's also like a low X physics. And the idea was really to also kill the CGC actually. That there was some predictions, and we tried to, you know, say, okay, they made some prediction, we do the measurement, and they will not be able to explain. But my kind of experience with the CGC is that they are always kind of able to adapt. I don't know, maybe we'll have some comment to that. Yeah.
You can explain anything, just cover those.
Yes, that's kind of yeah. So I'm not. Yeah. I think there was one question in the back.
Yes, a question about electric force. Could you show this next what was V2?
The V2. Yeah.
Yes, and what exactly do you measure in the final state? Is it included or you find some particular channel?
No, these are just particles.
No, in the final state you measure inclusive cross-section.
So this is actually not inclusive cross-section. So what you really do is that this is not even, you don't need luminosity or anything. What you do is that you look at every event and you look at the particles, how they are produced. Is there there is no board.
There is.
This is board, right? Yeah. Is there a pen?
Oh, no.
Okay. It's fine. I will. No. It's fine. I will explain on maybe here. Okay. So imagine that these arrows are particles. Okay. This is actually here is not particles, but imagine these are particles, and it means that there are a bit more particles produced like here, I don't know, here and here. So there's like it's like it has a triangle structure, okay, and there is more particles produced here, here, and here, okay. And then what you do is that there are a couple of methods how you can calculate, but you just measure a correlation between the particles that are produced. And the V2 is one of the like a factor component in the Fourier transform, the Fourier expansion of the particle production. Okay, so basically you measure, you can define some axes here, or here are multiple axes, like 3, and then you correlate the particle production with respect to like this axis. Okay, and if there is any correlation, it will appear as the non-zero V2. So actually you don't measure any like a cross section. What you really measure is that you just look at a single event, you analyze all particles with some PT, and you try to understand if there is some anisotropy in the particle production in this angle, and that's it.
Understand. So you basically do not impose conditions that, for example, you produce GSI or produce, for example, piles.
No, this is just some everything. Yeah. Every particle. You can do, for example, like these measurements and do it only for example, baryons or only for mesons. That's interesting. Or you can do it only for, I don't know, kaons and pions. But for example, with Atlas, we don't have ability to do the particle identification, so we do just everything. It tells you still a lot about the.
How does this value V2 compares with what you see in PP conditions or Kelvin conditions?
So it's actually here. So this is the V2 in these UPC collisions, and these ones are the PP collisions. The ion collisions are not here, but for example, in what we measured recently, the OO collisions, the V2 is at a level of I think like 0.2, so like here. Then it depends on the centrality, because if you have a very central collision, the V2 is small because it's very symmetrical. If you have like a more like a semi-central collision where the overlap region is like a very asymmetric, you get larger V2. Okay? So, but I mean, if you look at the LED, then yeah, I mean, it will be somewhere like out there.
Understand. Sorry, another question. As I can see, you impose conditions that this forward correlates environment. What's that? The theta.
Sorry, one more.
Question about the rapidity.
Oh, this one.
Yes, this forward frequency.
So this one is no. This is for. This is a rapidity gap, I think. So this is just how you identify. I have to take a look. No, these are rapidity gaps. This is cut. It's not. This is not definitely only like this is not about the particles where you measure them, but this is some characteristic of the event. I don't remember details now. I will have to look to the paper. Yeah, sorry. Yeah.
And maybe that one is to remove the non-flow contributions that you're looking for particles that are very far away.
Yeah, maybe, yeah. It's like how you correlate the particles. Yeah. Yeah, you apply a couple of cuts. So there is like this one, which is like you apply some rapidity gaps. So you require that some parts of the detector like empty. So you actually know that these are like photonuclear events. And then to like remove, because as I said, you measure the correlations, right? For example, imagine that you have a jet, right? And the jet is like a spray of particle, which is, it's correlated, right? You have a lot of particles in one direction, so they are correlated. And when you apply them, but they are correlated in the delta phi, in the azimuthal angle, but they are also correlated in the delta eta, right? Because it's a jet is a cone. But if you apply like a cut, that there is the distance between the particles in the eta is larger than 2, then it means that the two particles that you correlate together, they are not from the jet, right? Because they are like in the different parts of the detector. So it's like as Sebastian said, so this must be the how you select the particles that you correlate together.
More questions from the audience? Yes.
I have a question about the process. Yes. For example, gear production.
Which production? Sorry.
For example, gear production. Because in your only line by bytes, but if, for example, one universe exchange two gluons, you know, the exchange is not very surface compared to exchange. How would we experiment this separate?
Yeah, so you have it here, right? So I mean, here you have the light by light, right? And here you have the two loans, right? And so basically, you don't separate. There is always some contribution, but then if you look, it's basically here. So so in your data, you compare them to the model, and the red, this is like the gamma, and this CP, so this is your gluon to gamma. So you kind of see that it looks like this. So it's like, so if you have a gluon to gamma, actually the angle between the two photons is, the angular correlation is like much broader. But at the end, what you do is that you take all these different contributions that as you correctly said. I mean, it's there. It's just that especially in this part where the photons are really back to back, the contribution is small. But you take it and you subtract it, so it's taken into account.
More questions? We change the Zoom. The people who are connecting the Zoom. I think the people from the Zoom, no more questions from the audience. If there are no more questions, we thank the speakers for the very nice and very complete talks. Thank you so much, Martin.
But I think it was fine.
Video marks for students.
Hi, Martin.
Hi, sorry.
A table with the energies in the central momentum of different collisions. But I understand some of